this is our first one, just a nice warm-up one. When I look at that, I see the sign of something. So this guy here is like the g of x. The g of x is the something. So you differentiate the sine of something, you will get that cosine of that something, and then you finish with times the derivative of that something. And in some situations, the style points are really just rearranging the order. You don't really do much more. So, pretty straightforward one, no frills. Now, not every question is the same. So here is another question that is also going to use the general. It's 1 over the cube root of 4x squared take away 5. So if you're looking at a question like that and you're saying, well, how do I know it's a general? Typically, if it ain't an x, it's a general. So what do I mean by if it ain't an x, it's a general? If that was sine x, it wouldn't be a general. If that was 1 over the cube root of x, it wouldn't be a general. But the minute you stick something inside the square that's not ain't an x, right? A 2x plus 1, a sine x, a 4x cubed, then it's a general. The minute you stick something in the sign here that isn't an x, like a 2x plus 1, or a cosine x, or e to the x plus 1, or as in this case, x squared minus 1, then it's a general. So if it ain't an x, it's a general. That's kind of how I look at these things.
So a polynomial then? If you have
say again, Robin?
If you have a polynomial in there, then it's a chain rule. And if it's a single number,
X.
Yeah, then it's a normal.
Yeah, pretty much. So in this case, I'm going to start in a very similar way.
Can you say that one more time? So if it's an X, then it's not.
If it ain't an X, then it's a chain rule.
So
I'm trying to be American. Ain't. You say ain't. That's me.
An X.
It's a chain
rule.
Yeah. Okay. So in this case here, I have some extra work to do. I know it's a chain rule, but really I can't deal with 1 over cube roots. We're comfortable with that. Isn't that exactly what I would have done if it was 1 over the cube root of x, right? I would have rewritten it as a negative fraction in this case. So you want its derivative. It's something to the power of negative a third. So you multiply by the 3. So what do you get? Reduce the power by 1. Right. So something to the negative a third is negative a third, something's to negative 4/3, and then you finish with the derivative of the something. And then you make it look pretty. Well, I got a negative 8x on the bottom. I now have that. And in this case, to complete the style points, make it look like the original. So this is the final answer.
Should it still be an 8x on top of the final answer?
You all caught that deliberate mistake? Oh God, I wish I was good at lying. That was just a mistake. Okay, let's move on. Now, like every rule, I guess there was exceptions. Now, if I write it like that, can you see it ain't an x anymore? In this case, it ain't a theta. And you have to take trig powers and think of them as this. And it helps you to see that this isn't theta cubed or x cubed. It's a cosine theta being cubed. That makes it a general, right? It ain't an x. Now, I haven't done anything here except algebraically write it slightly different. So this is 3 something cubed. So you get 9 somethings squared times the derivative of the something. And the derivative of a cosine is a negative sign. And that's negative 9 sine theta cos squared theta. That's the end of that one. Now we're on to question 4, where more stuff is happening. The first 3 questions were just a single chain rule process, right? I could have done one of the Russian doll ones, but we've seen them and I don't want to do too many of them anyway. They take time. Once you know how to do a Russian, a Russian doll, a chain rule inside a chain rule inside a chain rule kind of question, right? So what we're looking at here now is not that. We're looking at a product rule. Now, when I look at a normal product rule, it's got 2 pieces, which this one does. And there's nothing too surprising about that. And then to get its derivative, it would be f dashed g plus fg dash. Again, nothing special. So where's the difficulty, or where's the chain rule going to prop up? Don't you need to differentiate the cosine of pi t? That is not the cosine of t, is it? Right, it's like cosine of pi x, right? It ain't an x. So pi x ain't an x. That's going to become important in a minute. Differentiate this, you get 6t. Leave the other guy alone, you get that guy. Plus, leave the first guy alone. And now, not much of a chain rule, but it's still a chain rule. Isn't this the cosine of something? If you differentiate a cosine, you get a negative sign of the something, followed by the derivative of the something. What is the derivative of pi t?
Pi?
Yeah, just like the derivative of 2t is 2. Remember, pi is just a number, so pi t is like 2t. Now, make it look pretty. Well, there's really not a lot I can do, but I'll try. Can't do anything to that. Looks good. Can do that, that, and that. So what do I get? Negative 3 pi t squared, the sine of pi t. So at least we didn't have too much in the way of algebra. Here's our next one. Right, so we're going to differentiate e to the ax cosine of bx. There's only one variable in this entire expression here, right? And that's x. The a and the b are representing what we call constants. In mathematics, a constant is a fixed number. And a is just representing some particular fixed number, right? So treat the a and the b like they were 5 and 2 or something, right? Think about them like that. Don't think about them in any other way. Just, it's like e to the 5x cosine of 2x, right? It's like that kind of question. This is a product rule. There's the f, there's the g. But not only is it a product rule, aren't we going to be using the chain rule inside that process? So let's see what we get. If you differentiate e to the ax, it's e to the something, right? So you get e to the something, right, times the derivative of the something, which is a. Then you leave the other guy alone. Plus you leave the first guy alone. God, they seem to be picking a lot of cosines today. Yeah. If you want to differentiate the cosine of bx, think of it as a chain rule. It's a cosine of something. So you get negative the sign of that something times the derivative of, which is b. And now I'm going to try and make it look pretty. I'm going to pull out e to the ax as a common factor. That's going to leave me with a, oops, it's going to leave me with a cosine of bx minus b sine of bx. It's a bit messy there, but you can imagine what I've written. So what I want you to get out of today is how the chain rule can be used in a multitude of different situations, and to be able to recognize that it is a chain rule, or at least pieces of it are chain rules. But that doesn't mean that you don't do the product or the quotient rule as well. There are questions where, like here, and right, where you mix and match two methods together. Make the variables match. Oh, darn it. Got to get my scanning sorted out. Wow. 3x plus 3 to the power of 5 and a quadratic to the power of 10, both being multiplied together. That is one ugly looking product. And it is a product rule, agreed? It's two things multiplied. That's going to be the F, that's going to be the G. Secondly, if that wasn't bad enough, there are going to be some other things, well, we'll see them in a minute, that are going to get in the way. I'm just rewriting it over here. I think I need more room. So it's going to be f dash g plus f of g dash. If you differentiate this guy here, think of it as something to the power of 5, right? Something to the power of 5 gets you 5 somethings to the power of 4 times the derivative of the something, which is 3. And that's just the f dash done now. Tag next door the untouched g plus the untouched f. And now do this fella. Something to the 10. 10 somethings to the power of 9 times the derivative of the something, which is 2x add 2. God, that was tight, even though I give myself room. You got all of this stuff plus all of that stuff. We need to go hunting for common factors because there's going to be some style points going on here. Right, look at this expression and all its pieces. Look at this expression and all its pieces. Start telling me some common factors because there's a lot in this one.
Could do a 3x plus 3 to the 4th.
Agreed. Go hunting for some more.
X squared plus 2x to the 9th.
Right. Now, if you look at these two numbers, they're basically 15. And if you look at this number in here, it's basically a 10. Can you see I can pull out a 5 as well? It was a little bit less obvious. Okay, I think I've got all the good stuff. Used up, still there. One of these still there. Agreed. Plus, not used up, one of them at least. 10, that's 2 of them, not used, all used up. and a 2x plus 2. So I have 5 lots of this guy. I'm going to just distribute this and hopefully, no, we'll see what we get. I'm going to get 3x squared plus 6x. 3 times that is 6x squared, but you double it. 3 times that is 6, 3 times that is 6, it's 12, and then you double it. And 3 times 2 is 6, and then you double it. It's just like a monster. It just keeps on getting bigger. Okay, that and that gets me 15x squared. That and that gets me 30x, and I got a 12. Okay, I guess it's nice. I'm being nitpicky here. Is there anything else, common factor wise, that I could now use in particular here?
A 3.
Yeah. So if I pull out another 3, that turns into 15. Got 5x squared, I get 10x, and I got a 4. Have a quick look at that. 5 with 4 doesn't play well. 2 and 1 doesn't play well. Right, we're good. That's the end of the line. Okay, that was a fair amount of work, especially just making it look pretty, which took more work than anything else. But if you consider the alternate, if you didn't do the chain rule, wouldn't that question be horrendous? I mean, what could you do? Well, I guess I could FOIL that out, times FOIL that out, and do a really huge polynomial times another huge polynomial and do a product rule on it. I think that would take a lot longer, and it certainly wouldn't look as pretty at the end. So even although it's a bit awkward, the chain rule still wins. Look at this guy. Would you agree it's a quotient rule? Pretty obviously a fraction. Quotient rule works. And won't the top end up being a chain rule, right? It's the sine of x squared, right? A and n x. So the derivative is f dash g, take away f of g dashed over g squared. We're right into the chain rule. I need to differentiate the sine of something. So I get the cosine of something times the derivative of something. And then I have to remember to tag on the untouched g. Take away the first guy, right, untouched f, times the derivative of g, which is just that. That's the calculus finished. I don't think there's much in the way of style points, but I do see something. Can you see anything I could do to the top line that might make it a little bit prettier?
Factor out 2x.
That's what I would do. And that leaves you with this and this guy, so I guess I'll put the x squared plus 1 first and the cosine later. Take away the sine x squared. Yeah, that one didn't require too much style points. Okay, any questions so far? Because we've kind of shot through these 7 pretty rapidly. Are we getting a little bit more comfortable playing with the chain rule, right? Doing questions that It might not just be the chain rule, it might be a product rule with a chain rule, or it might be an ugly chain rule, whatever it might be, but we can handle it. Okay, we're looking at 8 then. Oh, I'm doing 8 on a new page. Just looked at it. There is definitely a fraction there. There's no two ways about it.
Are those U's?
Yes. Definitely a fraction. So that means there's going to be a quotient rule somewhere. But it's a fraction to the power of 5. So this is a chain rule and a quotient rule. But it's the chain rule first and the quotient rule later. This was a quotient rule first with some chain rule stuff later. This is the opposite, right? So when I look at this, I see something to the power of 5, right? My fingers are covering the something. So when you're being on the derivative, it's 5 somethings to the power of 4 times, and I'm not even going to do it, I'm just going to write it down, times the derivative of the something. So if you want to differentiate this, it's 5 somethings to the power of 4 times the derivative of that something. So that might not be quite mathematical, but it gets, I think it gets across what I'm doing. Now, don't we need to just focus on differentiating this guy, right? The derivative of him. And isn't this guy the quotient rule guy? So that piece there is F, and this piece here is a G. So I'm going to be getting 5 lots of u cubed minus 1 over u squared plus 1 power of 4 times f dash g, take away f of g dashed over g squared. Are you comfortable about what I'm doing here? The order that I did it. It was a chain rule that we took care of first, and now we're about to finish off with a little quotient rule. Okay, top guy's derivative. Let's see what we get. Top guy's derivative is 3u squared times the untouched g minus, leave the top alone and differentiate the bottom, and the whole thing on the bottom gets squared. Well, I got a whole ugly mess out here. I could pull out a common factor. That may help. Do you think pulling out a common factor here might help, or could I distribute it and collect like terms? That would work. Actually, both will work. So whatever one you feel like. Do you want me to do it as a distribute and collect like terms, or do you want me to do this next line as a common factor? It really doesn't matter because they both work. What do you want to see?
Distribute.
Okay, so distribute this guy. You get 3u to the 5 plus, plus 6u squared. This guy times this guy, and then you subtract it, gets you take away 3u to the 5. This guy times this guy is -3, but then you subtract it, you get that. They kill each other off, and you have 6u squared. And things are looking good. But they're not. quite there yet. Well, I know I can multiply them together, but that's not what I'm getting at.
Shouldn't that be 9u squared because you have the 6 and the 3?
Yes. My brain's thinking of the next line as well, which isn't helping. Right, so you got this guy, right? And I'm saying I can do better. I can make this look a little bit nicer than it does. And the way I'm going to make it happen is to realize that this fraction to the power of 4 can actually be split. And then next door to it, I'll just write this guy again. And now 9 and 5 get me 45, u squared, u cubed minus 1 to the 4. And on the bottom, I can have a u squared plus 2 to the power of 6. And now we're finished. And this is considered nicer than that.
How did the u cubed plus 2 squared on the bottom turn into a u squared plus 2 squared?
This guy here, it came from the g squared, which is this guy being squared. F dash g, so you, blah, 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 blah. When you want to differentiate this fella, it's a quotient rule. And part of the quotient rule has a g squared on the bottom, which means this guy is squared. So if your question is where did that come from, that's where it came from.
Yeah, but it's
No,
squared instead of cubed in the inside the parenthesis.
It's squared instead of cubed.
Yeah, and the last
Oh.
step was u squared plus 2.
Yeah, in the last line it's cubed.
Oh, shit in space. I'm having a bad day today, guys. Somewhere. Every 2's a 3, basically. Thankfully, the rest of it is right. It didn't turn into a 2. I wrote it as a 2 for no reason I can think of. Okay, I'll give you a few
You're
moments.
definitely making my mistakes feel better.
Oh, I make many more mistakes than any of you lot do. I put it down to not just being careless, old age, and thinking 3 lines or 1 line ahead of myself, which is very dangerous because I'm already thinking about what I'm going to do next before I've even written what I've done. So you learn by those things. So here is question 9. The kind of ultimate version of that guy. So you lot are going to be on your most observant to watch out when I start going astray. So let's get started. How am I going to rewrite this thing to even begin thinking about differentiation? Because the way it's written right now, it's not going to happen. How should I write this guy?
Would you separate it into 2 square roots and raise each term to the 1/2?
Almost what you did, but with a little bit less. What do I mean by a little bit less?
Just make it so the whole expression is times to the 1/2 power.
Now, what Maggie said would have also worked, so it's not like she did the wrong thing. You would have got the same answer. I think it might have been just a little bit messier, but it still would have worked. Now, when you see this guy, doesn't he now look kind of similar to this guy? Isn't it ugly thing to the power of 5? This time we've got ugly thing to the power of 1/2. So the way I see this is, it's a something to the 1/2. Right. So it's 1/2 something to the power of -1/2 times the derivative of that something. Me personally, as you've already seen today, I need to kind of separate out things and try not to do too many things in my head. If you juggle too many balls in your head, you tend to drop things. Okay, so far so good. There are two distinct things that I'm going to do next. One here is I'm going to differentiate that. Would you agree that's just a quotient? No. Right. So I know I'm going to be doing on this side an f dash g take away f of g dashed over g squared. And this fella here, the whole thing, is going to be f, and all of this is going to be the g. That's fine. So that's that bit done. And over here, I have a big problem with a negative fractional power of a fraction. And I know I'm going to have to make this look pretty. So I'm going to do a trick. Can you see what I've done here and why it works?
Since it's a fraction being divided by a fraction, you essentially reciprocate it to,
And the negative cancel out,
Yeah.
and it's a plus. Isn't that going to look much prettier later on? Because wouldn't that just be the half of an ugly square root? Right, now let's focus back on this guy. So it's going to be 1/2 ugly square root. Kind of happy about that guy. Times, well, let's see what we get here. F dashed is the top, which is a cosine t, times the untouched bottom. Take away, leave the top alone, and differentiate 1 plus cosine gets you negative sine t. And that is going to be over a 1 plus cosine t squared. Right, distribute. I get a cosine t plus a cos squared t. Negative sine t times -1 gets me a plus sine t. And that guy, then that guy gets me plus sine squared. Oh, something. It's not a lot, but something happened. Do you see that cos squared plus sine squared? See him? That just gets me a +1. And stick a bracket around it. It's ugly. I can't see that becoming much prettier, so I'm not going to try. I could have split this into 2 square roots and maybe I've got a little cancel going on with this and this. But at the end of the day, it would be even uglier, I think, so I'm leaving it alone. So we have seen quite a huge variation in things that the chain rule can be used on. So let's just spend a few moments looking at homework questions. I think I'll bring them up. And I'll just start at the top. Right. Isn't that just something to the power of 6? Right, general. Something to the power of half, general. Something to the power of negative a third, general. How would you look at number 4?
Change it something of the power of -3.
And then it's a general. Agreed? Isn't that just the same thing as 5t plus 1 to the -3? Right? That would be a nice, better way of saying it. Something to the power of -3, just a general. So far, we're only doing generals, right? There's nothing else happening except generals. Right. Isn't this the cosine of something? So it's a general. Okay. How are you going to write cosine cubed theta so that you can see a general in it?
Cosine theta cubed.
So it's something cubed now.
Yeah.
It's a general. Exactly. Isn't that e to a something? So it's a general. Isn't this now a product rule? But in this product rule, isn't only that piece the piece that you end up using the chain rule on? Because you're going to differentiate that. You're going to get e to the -4x times another -4. Can you see a product rule? But isn't this piece the only one that's going to give you the chain rule? Product rule, but won't both of these involve a little bit of a chain rule? Product rule for sure. Would you agree that this piece here is a chain rule, and that guy there has to be turned into t to the half before you try and differentiate them? Right, the square root of t. But the square root of t is just a normal derivative, right? There's no chain rule needed for that. But the e to the something, that is different. There's the guy we just did. E to the something. Oh, we did something very similar to that, right? Did something very similar to that. E to the something. Do you see that the something here is going to involve a quotient rule later? So the answer is going to be e to that something times the derivative of that blue guy, the z over z minus x. That is going to be one ugly looking answer. I can tell right now that is not going to end well. Some answers are just ugly, right? And you just live with them. This fella here is e to the something. Do you see that the something is going to be a product rule this time? We've done one similar to that, right? I think the one that looks like that is this guy, right? So it's nice you see 2 examples. A product rule with this piece needing a chain rule later. A product rule where both pieces will need a chain rule. Do you know the derivative of e to the -x isn't just e to the -x? It's e to the -x times -1. Right, because the derivative of -x is -1. That's a something cubed. That's actually a Russian doll question because you're going to have to differentiate 7 plus cos squared, and cos squared is itself a chain rule. How would you write that guy, 23, so that you could differentiate it? Maybe I should do that one. While you're thinking about it, I'll write it down. So it's sine squared of x squared plus 6. I know it's a chain rule. I mean, it's, you know, it ain't got an x in it. It's got x squared in it for starters. My question was, how should I write it so that it's in a form that allows the chain rule to happen? Sine squared of this guy. No takers?
The sine of the something all squared.
Great. Maybe you knew that and you didn't think that's what I was asking. That's all I'm asking. Right? Don't you do sine squared, sine cubed, tan to the 4, secant cubed, things like that as the thing cubed, the thing squared, the thing to the 4, right? Now, from this perspective, it's going to be 2 somethings to the power of 1, which I won't bother writing, times the derivative of that something. So this is a Russian doll question. This is a chain rule with some more chain rules in it. Well, how do you differentiate the sine of x squared plus 6? It's a sine of something. So you get the cosine of something times the derivative of something. Do you see the 3 dolls, the Russian doll thing? The thing inside the thing inside the thing. Right, making it pretty, there's very little I can do to make this pretty. Can certainly do that. I could also do that. Where the heck did that come from? What happened to the 4? It turned into a 2. What happened to the sine and the cosine? They turned into a single sine of 2x squared plus 6's. What just happened there? Trig identity. Sometimes you can't see the forest for the trees. Isn't 2 sine A cosine A twice the sine of A? Can you think of that as being the A's? Can you see that's a 2A? Do you think I've used up one of those 2's and there's still 2x left? That's where that came from.
So we can factor out a 2 from the multiplier.
Yeah, the 4x. Yeah.
And then use it to do the trig identity for.
Yes. Sneaky. Don't see it often, but I'm probably more generous in a test. If I saw that, I would probably let it slide because it's not reasonable to assume that you would have seen it. But it's cool if you did see it. Right. Let's finish off by looking at just a few more of those homework questions. We're almost at the end. Right. In question 24, this is going to be a chain rule plus another chain rule. In fact, these chain rules are Russian dolls because there's a chain rule inside the chain rule in each case. Oh, there's a really cool Russian doll. The tan of a secant of a cosine. That's almost like Elizabeth's. Oh, let's finish that one. We have 3 minutes. We can do that for our last question then. We're going to do the tan of the secant of a cosine. This is a good Russian doll. This has got chain rules inside, all sorts of chain rules. So as long as I keep track of whereabouts in the Russian doll I am, I should get through this and survive. It's a tan of something, agreed? That's the first level. The tan of something. the derivative of a tan is the secant squared of that something times the derivative of that something. So tan of something, secant squared something, derivative of something. All right, let's do the derivative of secant something. What's the derivative of a secant? Hopefully you've got it in your brain now. Derivative of a secant.
Secant times tan.
tangent.
Right, so the derivative of a secant something is secant something tan of something, finishing with the derivative of the something, and the derivative of a cosine is negative sine t. And all I'm going to do now is make it look pretty. The negative, then the sine, then the secant guy, followed by the tan guy, and finish with the secant squared guy. And if you could figure that one out, I don't think there's a chain rule you need to worry about. Can you imagine I did that as the first question yesterday? Wouldn't you be running out the room screaming right now? Right. See, I hope anyway. Do you see the difference a day can make? Yeah, the more practice you get a chain rule, the less scared you are of weird looking functions, because you just see them as just chain rules, or chain rules inside chain rules, you know, occasionally.